In this video I will explain the concept of discriminant validity. I will not go in detail into the different techniques that we can apply to assess discriminant validity. That's a topic for other video. But we need to understand what the concept is about to be able to pick a technique and then evaluate or interpret the results from that technique. So the conceptual understanding is the key to successful use of any statistical technique. Let's take a look at what discriminant validity is. So discriminant validity is often presented together with convergent validity, and that relates to the history of these two terms. They were originally presented by Campbell and Fisk in 1959, and they were presented in the context of multi-trait, multi-method matrices, and this was presented as a validation procedure. But they never defined what convergent validity and discriminant validity mean outside multi-trait, multi-method context. The current practice is that convergent validity is used to refer to whether indicators that are supposed to measure the same thing correlate highly, and discriminant validity is commonly used to refer to whether a correlation with these scales is so high that those scales can be interpreted to measure two different things. So let's take a look at how discriminant validity is being assessed currently. I and Joe went through a few years of AMJ and JAP, and then full history of ORM and see how these how discriminant validity was actually empirically assessed in these papers. We found about 20 different techniques, and if this was a toolbox and every tool had a specific purpose and was used for that purpose for which it was optimal, then this would be an ideal scenario. But it's not like that. It's more like a collection of parts or collection of tools, and people seem to pick on random which tool they apply. Some of these tools are not really well suited for the purpose at all, and some of them are easily misused. So this is a bit of a mess, these techniques, because it's very difficult to say based on existing research which of these techniques is best, why, and under which scenario. There is also a confusion around the definition of discriminant validity. When we talk about discriminant validity, what do we actually mean? So we found basically 4 different classes of definitions, and then the first class could be further divided into 2 subclasses depending on whether we interpret what the author writes literally, or whether we try to interpret what the author might mean by what they write. The first group is a correlation between constructs or estimated correlation between constructs. So if discriminant validity refers to constructs, the conceptual variables, then discriminant validity is something that exists independently of measurement, and as a consequence, for example, discriminant validity problem couldn't be addressed by developing better measurement procedures. If on the other hand it's about estimated correlation, then it concerns estimation procedures and measurement procedures, and maybe the constructs themselves. Another group of researchers think that discriminant validity is correlation between measures or the items. So it's more related to the data than what the data are measuring or what representations we construct from those data. Then there is this kind of definitions that are closer to factorial validity, whether items measure what they're supposed to measure, not something else. And then there's the 4th class, which is a combination of categories 1 and 3. So people don't seem to agree on what discriminant validity is about, and I think the reason for this is that it was originally presented without a definition, and then people tried to come up with different procedures, and then infer from those procedures what they might actually be able to assess. So to make sense of all this mess, Joe and I wrote a paper about these 2 organizational research methods, and it's open access. You can download it from the journal website or using this DOI number here. And in the paper we go through the definition of discriminant validity. So we go through the history of the concept, how it's currently applied, and then we synthesize the current understanding and current meaning that researchers attach to this concept as a definition. And then we go through all the statistics that we could find, or most of them that we could find, and test how well those statistics are able to assess the concept that we present. So starting from trait multi-method matrix, we need to understand that the key idea in discriminant validity is that it is about a correlation that should not be too high. So too high correlation between items is evidence of a discriminant validity problem. And we have also M1 and M2 are maximally different methods. What researchers have been struggling is how do we generalize this concept of discriminant validity presented here as a set of rules of thumb, how do we generalize it to other contexts? So we are not the first researchers to analyze this definition, but our paper currently is the most modern take on what discriminant validity might mean in contexts other than multi-trait, multi-method matrix shown here. And this is our definition. How we come up with this definition is explained in detail in the paper, but we define discriminant validity as a property of item or scale pair. We call these items or scales as measures. So a measure can be a collection of items or it can be a single item measure. Two measures that are intended to measure distinct constructs have discriminant validity if the absolute value of the correlation between the measures after correcting for measurement error is low enough for the measures to be regarded as measuring distinct constructs. Why is measurement error important here? It is important because discriminant validity originally was motivated by Thorndike's observation from 1920 that if there is a high correlation of 0.5 or 0.6 in two survey items that are supposed to measure two different things, then that indicates a problem because the correlation is affected by unreliability. So you will never get a perfect correlation because of unreliability. So correlation in the 0.6, 0.7, 0.5 ballpark can be problematic because then the correlation, if there was no measurement error, would be extremely high. And then it would be difficult to argue that those two items measure two distinct constructs. So we need to take the effect of measurement error into account because a low correlation between items can be not only because the items measure two different things, but it's also possible that the items measure the same thing and they're just unreliable. For example, if you have items that depend linearly on the same common factor and the factor loading is 0.7, then the correlation between the items is going to be 0.49. And that would be a problem if we would want to claim that the two items measure two different things. So discriminant validity is about measures, not constructs. If we go back to the slide that I showed before about definitions, there was some confusion about constructs and measures. Is discriminant validity about measures or constructs? Our position is clear, it is about measures. So it's one part of measurement validity. It's not about whether constructs are valid or not. Constructs are how we define what they are. So there is no, the validity is a measurement concept, it's not a concept related to constructs themselves. And also another important thing about our definition is that many of the prior definitions relied on factor analysis or factor model as a part of definition of discriminant validity. So basically the original problem was with discriminant validity was that the definition was tied to a particular empirical procedure, multi-trait, multi-method matrix, and then researchers have proposed to solve this problem by introducing a dependency to another technique that is more commonly used. But that's simply switching the problem from one domain to another domain without actually solving the problem itself. But this definition, of course, applies to common factor models, and because most of the time what people use for measurement validation is a factor analysis, we present the application of this definition in the context of common factor model. So this is the common factor model in matrix notation. If you don't understand what the equation means, that's not terribly important for understanding the point that I will make. So we derived two different ways of assessing or defining discriminant validity in the context of common factor model. We can first define discriminant validity according to the equation 2, in which case we compare each correlation between each item pairs that are supposed to measure two different constructs, and we check that the correlation is low enough after considering measurement error for those two items to be considered distinct. So if the correlation between two items that are supposed to measure the same thing is going to be 0.5, then because of measurement error or unreliability, then any correlation between items that are supposed to measure two different things should be well below 0.5, 0.4, 0.35, something like that. So this is the item level definition in the context of factor model. And this is something that we have not actually seen anyone apply. So currently the researchers, when they assess discriminant validity, they always focus on the scale level, not on the item level for some reason, even if the original definition focused on items. Then we have this monstrosity here, which basically says that two factors estimated from the data that are supposed to represent two different constructs, their correlation should be well below 1. How much is well below? That is something that I will address a bit later in this video, but this is pretty much compatible with all the current practices that rely on estimating factor correlations, checking their confidence intervals, doing nested model tests to see if a model with a factor correlation constraints to be 1 fits the data worse than the competing model where the correlation is freely estimated. So this is compatible with existing research practice. So equation 3 could be also understood in this way. Two scales intended to measure two different constructs have discriminant validity if the absolute value of the correlation between the latent variables estimated from the scales is low enough for the latent variables to be regarded as presenting different or distinct constructs. So this is the idea. You estimate a correlation between latent variables. If the latent variable correlation is low enough, then you conclude that those latent variables can be used as presentation or representations of different constructs, and therefore the two scales measure two different things. Okay, let's go back, and now our definition here contains the term low enough. So typically researchers want to test for a point hypothesis. We want to test if regression coefficient is statistically significantly different from 0. And the similar point hypothesis here would be that we want to test if a correlation is exactly different from 1, but this low enough is something that many people don't like. So we would like to have a strict limit, and anything above that limit is a problem, anything below that limit is not a problem. So how do we define low enough? So that's a very imprecise definition, an imprecise term, and it's imprecise for a good reason. We don't think that there can be one cutoff that is the right thing or the right for every possible scenario. So let's take a look at different magnitudes of when a high correlation could be perfectly acceptable, when a low correlation could still mean that there is no discriminant validity, at least in the sense that the two scales measure two different things. Our first example in the paper of a high correlation that is not a problem is the correlation between gender identity and biological sex. So we simplify things a bit here, and we assume that these are binary. So we assume that gender identity is either man or a woman, and biological sex is either male or female. So it's not as straight, but as clear cut, but this is a simplification. If that is the case in the population, according to APA, the correlation is going to be more than 0.99. Does it mean that a measure of biological sex and gender identity, if used as a measure pair, that pair can never pass any discriminant validity tests? Of course not. So sometimes high correlation should be tolerated when they're expected. So if we have really well-defined concepts if we know from existing theory that they should be highly correlated, if we have a large sample size and high quality measures, then having this high correlation would not be a problem. So we can't say that all correlation greater than 0.85 are always problematic, all correlation less than 0.85 are always okay. So it depends on the context. There are probably some rules of thumb that apply to abstract organizational level constructs, but there are always exceptions, and that is something that we need to understand. So categorically saying that correlations, let's say, are above 0.9 are problematic would be counterproductive for example, discrimination research. On the other hand, a low correlation does not necessarily indicate that two scales or two measures measure distinct things. And consider the example of two thermometers. One is limited to positive temperatures, another one is limited to negative temperatures. And the temperature varies around 0. So these two thermometers measure the exact same thing. They both measure the same temperature, but they're just calibrated on different ranges. And for that reason, their correlation is going to be about 0.45, even if they measure the exact same thing. So this is an example of two measures that measure different parts of the construct continuum, like Tay once likes to call it. And when that happens, we need to consider also the context of the measurement. So is it possible that our scales are like happiness scale and sadness scale, which could be considered as being on the same continuum of mood? Is it possible that we have math scores, math exam or tests, math questions in tests that have different levels of difficulty? So some of those discriminate well between good students and the best students, and some of them discriminate well between the worst students and the mediocre students, but those don't really correlate that well because they have the same problem as the thermometers here. So a small correlation does not necessarily indicate that two different things are being measured. So when you pick a correlation, when you consider what is low enough, that is not something that can be considered without taking the research context into consideration. So let's summarize this conceptual part about discriminant validity. This is our definition. Two measures intended to measure distinct constructs have discriminant validity if the absolute value of the correlation between the measures after correcting for measurement error is low enough for the measures to be regarded as measuring distinct constructs. It's important to not confuse this with factorial validity or item discrimination. So factorial validity basically refers to whether an item measures what it is supposed to measure and not something else. This is a term that predates discriminant validity, and if the original authors wanted to say that discriminant validity is more like a generalization of factorial validity, they have probably said so. It's also, discriminant validity is also different from item discrimination. So item discrimination refers to if, let's say, a math exam or some other item can discriminate between high and low performers. So how certain can we be that a person who does not know math will not get the question right, and how certain we can be that the person who knows math will get the question right? So this is about item discrimination. It's not about discriminant validity. And item discrimination is commonly discussed in works on item response theory. Also, unexpected high correlation can indicate a problem, but it's not necessarily always a discriminant validity problem. And this is a particular case if you have two constructs that should not be related at all based on theory. So based on theory, we should expect that two constructs are correlated at 0. Yet we observe a moderate correlation of 0.3 or 0.4. The two scales, the measuring these two constructs are clearly distinct because 0.4 and 0.5, 0.4 and 0.3, they are not close to one at all, but they're sufficiently different from the theoretical expectation that we should consider measurement problem a possibility. So it is possible that you have a validity problem, there is some kind of contamination that causes a shared variation between two items, for example, common method variance, that makes a correlation to be larger than expected, but if it's well below 1 or well below whatever cutoff you want to use, then it's not a discriminant validity problem. It's some other kind of validity problem. We also propose in our paper how you should assess discriminant validity. I'll talk about these techniques in a different video, but briefly we propose a classification system. So instead of having these rules of thumb of saying that correlations greater than 0.85 are always bad, 0.85 or below always good. If correlation is non-significantly different from 1, then it's a problem. If it's significantly different from 1, then it's not a problem. So instead of looking at that, we recommend that authors start to think about different degrees of a problem. So discriminant validity is not a yes or no property. It's a matter of degree. But for practical purposes, we introduce a classification system consisting of 4 levels: no problem, marginal problem, moderate problem, severe problem. And then we recommend 2 different techniques for assessing it. Either do a confidence factor analysis and check whether the upper limit of the confidence interval of a correlation falls below a threshold or above a threshold for negative correlations. And we propose also another system for doing nested model comparisons to accomplish the same. This is more complicated, but it is slightly better statistically, but I would go for this technique because it's easier to apply and it's also less likely to be misapplied. But my final point in this video is that these cutoffs, so we present some because we want people to apply these techniques because I think these are better than current techniques, but these cutoffs, like any other cutoffs, are completely arbitrary. So this is basically just based on something that researchers have thought that 0.8 might not be a problem, 0.9 might be a problem, but it's not like something that is written to a Bible or any other holy book. We should have a freedom to go with other cutoffs and other benchmarks if there's a good theoretical reason to believe so. Like, for example, if you're studying the correlation between gender identity and biological sex.